Okay, so let me start with some introduction. So I will talk about explicit boundedness of canonical Fano three-fourths. Yeah, I think yeah, I'll start with a definition. So I will work over the complex number field, and we call a normal projective variety X a Q Fano variety if minus K is ample. And we said that it is a weak Q-Fano if minus K is an F and B. I think this is a very classical and important object people are interested in. I think yeah, there are many experts in the audience and also in UK. And according, of course, we know that according to the mean model program, such varieties they are in a fundamental class in birational geometry as building blocks. So maybe I will give some very easy example. Like the most easy, the easiest example is the projective space Pn, and also some the hypersurface with low degree in Pn is also Fano. And also in dimension 1, there's only one, which is just the projective line. And in dimension 2, there are classifications like P1 cross P1, or you blow up P2 at most 8 journal points. This is the full classification. And also for weak Fano, then you should add the second Herzbruch surface, and also maybe you make the different definition for the journal points. Then you get weak Q-Fano surface, which is also called the weak Delpedo surface. And also in dimension 3, there are it's also classified for smooth Fano varieties. There are exactly 105 deformation classes for smooth Fano 3/4. And this was done by Skovitsky and Molly and Mukai in around 1986 or something. Yeah, before 1990s. So then, of course, one may ask what happens in higher dimension or the more singular ones. So this is our goal. Actually, it is very hard to classify all Q-Fano varieties, right? So we know that even in dimension 3, it is not easy already. Okay, so then, but what we want to do is that just we want to look at what happens in higher dimension, or for more singular Fano varieties. So in this talk, as the title suggests, we may mainly interested in singular ones, but we are still in dimension 3. Okay, so let me define the singularities we are interested in. So in general, we take X to be a normal variety such that Kx is Q Cartier. Then we can detect the singularity of X by looking at the resolution. Okay, so we take a resolution y to x, and we compare the canonical divisor, and then we can write this canonical bundle formula with some example divisors. Then the coefficient of the divisors tell something about the singularity of x. And we say that x is terminal if all these coefficients is positive. Okay, so and we say that the canonical if all the coefficients appear in the example divisors, they are non-negative. Okay, so this, I think this definition is due to Miles Reed, and in dimension 2, terminal just means smooth, and canonical means dual singularity. So they are of course important singularities for surface theory. And it appears naturally, very naturally, in the minimal model program, right? So we know that if you run minimal model program for smooth Fano varieties, then you will naturally get terminal singularities. Okay, And also one advantage of we're working with terminal singularity in dimension 3 is that it's fully classified by Molly, and we have very many tools to use, such as the orbifold Liman formula or something. Okay, so this is the singularity. And then we have a theorem by Kawamata and Kola, Mori, Takaki, and Bierka in journal, which says that if we fix a positive integer d, then the set of all canonical weak Q-Fano varieties of a fixed dimension d is in a bounded family. Okay, that means basically you have only finite many deformation classes for such kind of varieties. Okay, so this is actually proved in dimension 3 by Kawamata and Kola, Mori, and Takagi, and in any dimension is by Bierka. So the importance of this theorem just tells us that actually it is possible to classify all weak Q-Fano varieties with canonical singularities in a fixed dimension, right? Because we know that there are only finitely many families. So in any sense, it should be classified in the end. But of course, this is a very difficult problem. I think even in dimension 3. Okay, so then let me just explain a simple goal up to now is that we could try to study explicit boundedness of environments, and then we can try to classify the extremal cases. So this is like we have a map and we want to know where is the boundary of the map, and we try to detect the objects sitting on the boundary. So this is like, yeah, I think maybe the very naive approach to the first step of the classification. And today, what I'm interested in, or what I want to talk about is two environments. Two environments we are interested in. One is the anticanonical volume. So just the self-intersection of the anticanonical divisor, and the other one is the anticanonical system minus MK. So we know that, for example, this degree is a very important environment for Fano varieties. For example, in the classification of Fano smooth Fano threefold, we should also study this number. Right? So when we want to classify the smooth Fano threefold. Okay, so then let me start with the anticanonical volume. So then the basic problem for this anticanonical volume is just this is a number, right? So then what is the lower bound and upper bound of it? So if we can first step is we want to control it from below and up, right? And then we try to classify all the values in between. Okay. So then for the lower bound, actually there's a very nice result. This is actually I think the first explicit result for Fano threefold with canonical singularity or with terminal singularity. So this is proved by Chen and Runkai Chen in 2008. So their result says that if X is a canonical weak Q Fano threefold, then the volume is bounded from below by this number 1/330, and this is actually optimal. So we can take the equality. The equality holds. The equality holds. We know that the equality holds if and only if that X has a same Hilbert series with this weighted hypersurface. So this is X66 in the weighted periodic space P156, 22, and 33. So this is the last example in Yano Fletcher's list of weighted hypersurface Fano threefold. If you know that list. So this Rongkai Chen and Meng Chen's result just tells us that the lower bound is this number, and this number is attained for this hypersurface. Then there's a natural question to ask is, can we characterize the extreme case when the volume holds when the volume attained this minimal number? Okay, so a more precise question is that is this always a deformation of this hypersurface I showed you, this X66? And actually, I give a partial answer to this question. So in a smaller category, which I just consider Q factorial terminal Q Fano threefold with pickup number 1. Of course, we know that this is also a very important class of Fano threefold, right? It belongs to the category of Morley fiber space. Okay, so then and also we know that any journal this kind of hypersurface it satisfies this condition. So then my result says that so if X is a Q factorial terminal Q Fano threefold with pickup number 1, and if its volume attains the minimal one, then X is always a hypersurface of degree 66 in this projective space. So that means if it has a minimal volume, then it should just be such kind of weighted hypersurface. Okay, so this is actually so last year I showed this theorem assuming that X is non-rational. So it's not birational to P3. But this week I just dropped that condition so to get this this new result. So we don't need to assume that X is non-rational anymore. Okay, so then, and in fact, we can do the same characterization of such kind of hypersurface in Yano-Fletcher's list. So then let me give you more precise statement. So say X is if X is a Q factorial terminal Q Fano threefold with pickup number 1, and if X has the same Hilbert series as some hypersurface of this form in Yano-Fletcher's list. So as you can see, when D equals to 11, this is the example with the minimal volume. Okay. But there are actually 12 examples in Yano-Fletcher's list satisfying this form. And then we can show that if X has the same Hilbert series as this hypersurface, then X is actually a weighted hypersurface of the same type. Okay, so that basically tells us that if numerically X looks like a hypersurface, then X is actually a hypersurface. Okay. Yeah. So then let me give some idea of the proof. So the steps. So actually the proof, the idea of the proof is somehow straightforward. So we just try to embed X in this weighted projective space, and show that it is actually a hypersurface of a certain degree. Okay, but in the first step we cannot get embedding, but we can get some rational map. So we just take journal element in the how to say the global sections of minus mk for m equals to this certain number 1a, b, and 2d and 3d, and then by this by this element actually we can define rational map, just like we define a rational map by global sections of a line bundle. But here, as the weights are different, so what we get is a rational map from X to weighted projective space instead of to the just Euro projective space. So we get a rational map like this. We call it phi. Okay, so then we study the geometry of phi, and actually we can show that a phi actually defines a rational birational map from X to its image, and we tell the image is Y, and then as you can see, Y should be a hypersurface of this weighted projective space, but we should also show that, oh sorry, here is 60. So we should also show that the degree of Y in this projective space is 60. So sorry, here is 60. Okay, so here you may wonder why this is true, and I can give you some hint. Is that by a result of Chen and myself in 2016, we can show that this linear system, minus 2dkx, it defines a generic finite map of degree 2, and this minus 3dkx defines a birational map. And then you can imagine that here we take some general section of them, and then eventually this 5 section could give us a birational map from X to this weighted projective space. Okay, so this actually depends on some geometry of X. And then finally, we should show that this X is actually isomorphic to its image Y by just looking at the Hilbert series. Okay, so this is some basic idea, but I cannot tell more detail. But if you are interested, please look at my preprint in archive. Okay, so any questions so far? Okay, so then let's move on to, this is about the lower bound and the varieties attending lower bound. Okay, but how about the upper bound? So for the upper bound, actually the situation gets more complicated because we very good upper bound until now. So here I gather some partial results. For example, if X, this is Kola, Miyawaka, Mori, and Takagi, they show that if X is a terminal weak Fano threefold whose anticanonical map is small, then they have this upper bound, which is quite big. You can see, and their method is they use a Benham rubric, and if you assume that X is Grunstein and terminal, then the upper bound is 64. So this is optimal. This is due to Namikawa by study the deformation of X. So he showed that such X is also always smoothable. So then the upper bound of the volume is the same as the smooth Fano threefold, which is just P3. And then Prokhorov, he dropped the terminal condition. He showed that if X is Grunstein and canonical, then the upper bound is 72. And it is also optimal because he showed that the equality holds if and only if X is this two-weighted projective space. Okay, so his method, he just use minimal model program and success of links, I think. Oh, sorry, no, maybe in this, yeah, he only used MMP, and so for non-Grunstein case, it's also a Prokhorov result. So he showed that if X is non-Grunstein, but he assumed that Q factorial terminal and P number 1, then the upper bound of the volume is 125 or 2. And also this number is optimal because it's attained by this weighted projective space. And in this case, he used MMP and also success of links and Limarot formula. Okay, so then recently, Qingrui Lai he generalized the Prokhorov result to Picard number 2, and he showed that the upper bound should be 72, except some case he cannot deal with. So eventually his upper bound is 81, and also he used the MMP and the soft links. But as you can imagine that so all this method above is not good in order to treat the general case. For example, band break and deformation are not good for singular varieties, and so in Grunstein case, MMP works because if you run MMP for a Grunstein Fano threefold, then you will always get another Grunstein Fano threefold in some sense. So then it's not so hard to reduce the problem to lower Picard number case. And in Picard number 1 case, so the key method is to use successive links to compare different modifier space, and this is also not good if we want to treat a general case. For example, when the Picard number is bigger than 2. Okay, so then up to now, I mean, before this result, we don't have a very good explicit upper bound for the volume. Of course, we know the existence because we know boundedness, but we don't have explicit value. And I should mention that conjecturally it should be 72, as in the Grunstein canonical case. Okay, but up to now there's no explicit bound. So then the result of myself and Yu Zou shows that we can give the first explicit bound for the anticanonical degree. So we show that if X is a canonical weak Q1 threefold, then the volume is bounded from above by this number, 324. So it's not so far from the optimal one, I think, comparing to the I mean, for example, comparing to the Collar, Miyaka, Molly, and Takais bound. Okay, so then and also a correlate that we can give an upper bound for the genus. So the H0 of minus K, so it's bounded by 164. So in general, if you are familiar with Prokorov's result, so in general, his method is first we control this genus, and then by the genus we can control the degree. But our approach is in the reverse way. So we first we try to control the degree directly, and we try to control the genus. Okay, so then let me give some remark. So in my PhD thesis, actually, I give a general strategy on how to bound the upper bound of the anticanonical volume of Q-Fano varieties with prescribed singularities. For example, with epsilon LC singularities. So I can show that if we have a weak Q-Fano threefold with epsilon LC singularity, then there is a number m epsilon, depending only on epsilon, such that the volume is bounded from above by this number m epsilon. And here the canonical just means one LC. Okay, so the problem is that we're trying to make my strategy as explicit as possible, because in my thesis I can only show the existence, but not it's not a computable number. Okay, so also by our same strategy, I mean the same paper, by the same strategy we can give an explicit bound for this m epsilon, depending only on epsilon. but not as good as this 324. So we also use some special property of the canonical singularities. But anyway, we have we have explicit expression for this m epsilon. Okay, but let me just focus on a canonical Fano threefold. Okay, so then let me explain our strategy, how to bound the degree from above. So first, we have some reduction step. So we change X to another model, to a model as the following. So consider X to be a canonical weak Fano threefold, and we can show that X is always birational to another threefold Y with the following property. So first is X Y is a Q-fat toroidal and terminal, and also we know that the volume of X minus Kx is bounded. Is bounded by the volume of minus Ky. So here Y is not necessarily Fano, so we use the volume of the divisor instead of the self-intersecting number. But anyway, we get some control of the volume. So from this condition, you can see that in order to bound the volume of minus Kx, we only need to bound the volume of minus Ky. And the third is that by changing the model, we know we don't have the condition that Y is Fano anymore, but somehow it's not so bad. So we know that the minus Kn Ky is movable, a movable system for some sufficient divisible n. And also we know that for a journal member in this system, then this pair Y and 1 over Nm is canonical. So this is like a canonical Calabi-Yau pair. Okay, so that means Y is not far from being Fano. Of course, it's not Fano itself. And also we have some fibration structure. So we have a fibration from Y to S with 3 possibilities. So here S when S is a point, then Y itself is a Q Fano threefold with P number 1. And when S is dimension 1, then S is P1. And the journal fiber of this fibration is a smooth weak dipole surface. And when S the dimension of S is 2, then we know that the S itself is a dipole surface with at worst dual singularities, and the peak number of S is 1. And of course, we know that journal fiber of this fibration is just a P1, because we are in the Fano type case. Okay, so this is the proposition, and the proof is actually not so difficult. So starting from, as I draw a picture here, so starting from X, we can do a terminalization to get a terminal X prime. And then we run MMP to get a Molly fiber space from Y to T. So in this case, if the dimension of T is 0 or 1, then we already have these 2 cases. So we take T to be S, and we are done. But if the dimension of T is 2, then we get T the surface. Then we still need to run MMP for T to get a new outcome of the MMP. So then we know that it's either a curve, so this is the second case, or it is some surface of peak number 1. So this is the third case. And then we consider the fibration from Y to S in the end. So this is actually the strategy of the proof this proposition. Okay. So then from this proposition, we can discuss. We know that in order to bound the volume of X, we need to bound the volume of Y. then we can discuss by the dimension of S. So if S dimension of S is 0, then we know already by product of the result that the volume is bigger, is bounded by 64. Then we are done. And then the interesting case is when dimension Z is 1 or 2. So then in this case, so we get a non-trivial fibration. And this fibration will help us to bound the volume in the end by some induction method. So say if the dimension S is 1, we show this is our result. We show that it's bounded from above by 324. And if the dimension S is 2, then the volume is bounded from above by 312. Okay. So let me explain the strategy, how we do this. So let me say, I'll just explain the case when dimension S is 1. So if the dimension S is 1, then the strategy is that if we assume that the volume of minus ky is big enough, very big, then we try to use the volume to construct the singularities on F. So F is the journal fiber of this pi. Okay. So this involves the so-called connectedness lemma. And then on the other hand, so we know that F itself is a smooth, weak diapason surface. So that means the singularity of S of F is not it cannot be too bad. So that the singularity here, I mean the singularity come from minus kf. So this is related to the lower bound of so-called log canonical threshold or the so-called alpha invariant. So for the first step, we know that if the volume is very big, then the singularity of F can be very bad. But the second step, we show that the singularity of F cannot be too bad. Then there's some contradiction, which tells us that the volume cannot be too big. Okay, so this is the basic idea. Let me explain in more detail. So how much time do I have? I think 30 minutes around.
You can have 25 minutes or so.
Okay. So say suppose that we consider the volume is bigger than 36 times the square of kf. So then we know that there exists some rational number s such that the 3s k square is between this number, between these two numbers. Then from this inequality, that means so this is the first inequality. We know that so this volume, the volume of minus ky minus sf, is bigger. So bigger than the difference of these two number, and which is positive. So that means this divisor is big. This divisor is big. So then that we know that there exists some effective divisor D, which Q linear equivalent to minus K minus SF for some S. Okay. So then we can consider a pair like this. So remember that Y and 1 over Nm. So this is actually the canonical Calabi-Yau pair on Y. So here M is a journal member in minus nky. And then we just remove, we subtract a little m, and we add this d and some f1 plus f2. So these are two fibers of the fibration. And you can see that this pair is still a Calabi-Yau pair. So it's the sum of them ky plus the lower this divisor is q-linearly trivial, but it has two LC centers. It has two LC centers, F1 and F2. But we know that these two centers are disconnected, right? But according to the connectedness lemma, we know that the LC center of this pair it must be connected. So that means we should have some horizontal LC place, right? So then we know that after restricting on the journal fiber, the journal fiber should be not KLT for this pair. Okay, so that means restricting on a journal fiber, by Bertini. So this pair is still canonical because on Y is canonical. But this pair is not KLT because, as we argued, it has a horizontal it has a horizontal LC center, and restricting on journal fiber, it is still when it's not KLT, it's still not KLT. And looking at these two divisors, we know that so of course here F is a weak diagonal surface, smooth weak diagonal. Okay, and we know that this two divisors are all Q linear equivalent to minus K. So this is somehow just a problem of a log canonical threshold, right? So that means from the beginning we have a canonical pair, but if you decrease this boundary a little and you add a little this 2 over S, then it becomes non-KLT. Okay, and both divisors are Q linear equivalent to minus K. So somehow this will tell you that this 2 over S cannot be too small, right? Because a small perturbation of canonical pairs should be canonical. Then our goal is to tell you how small how big this 2 over S could be. So this is actually a log canonical threshold type problem, and our main contribution is that we show that in this case, this 2 over S cannot be too small, but it must be bigger than 1 over 6. Okay, so this is one of the key contribution of our paper. This is 1 over 6. So which tells us that actually this S is bounded from above by 12. Okay, but here by the construction, remember that the definition of S is as this. Then by construction, S should be bigger than 12. So this is a contradiction. Then that means from the beginning, this assumption is wrong, right? So then the volume should be bounded by this 36 K to the square. And we know that the K square of F is bounded by 9, so this number becomes 324. So this is basically the proof. Of course, this is not optimal because as I said, we expect the optimal upper bound is 72. But I think this number is the limit we can get. I mean, it reaches the limit of our method. But if someone can give new ideas or new methods, then it might be possible to improve the bound. Okay. So when I say the limit, because I think this theorem, so the lower bound 1 over 6 is not improvable. So then the method is not improvable, I think. Yeah. Okay, so this is the upper bound of the volume, and then in the following time, I will talk about another topic, the anticanonical system. So for the anticanonical system, we have three main interests of the problem. So the first problem is that when the minus mk has a global section. Okay, when it's bigger than 0, right? So this is a non-vanishing problem. And actually, the second one is more interesting. Is when it has at least 2 linearly independent sections. Okay, so this means that the linear system defines a non-trivial rational map. Okay, and the final question is when the linear system it defines a birational map. Okay, so such kind of question they described how big the linear system is and how the behavior of the geometry of the linear system, or how the linear system will give us interesting geometry of X. Okay, so then let me explain what we know about this result. So first, when in 2008, the same paper of Meng Chen and Rongkai Chen, so they show they answer the first two questions. So they said that when m is at least 6, then minus mk is non-trivial. So it has a non-trivial global section. And when m equals to 8, then the h0 of minus 8k is at least 2. And this result is optimal. So we know that we know for example this example, this is in the Yano-Fletcher's list. So it's a complete intersection in a weighted projective space. And in this case, in this example, minus 7kx is 1. So that means you need at least 8kx to have 2 linearly independent sections. Okay, but for the first question, we don't know the right answer, because as far as we know, there's no single example of Fano threefold with terminal singularity such that minus 2k has no global section. So that means it might be possible to improve this m to 2, but we don't know. Yeah, for example, if you are familiar with the Riemann-Roch formula and the basket, one can show that there are some information, I mean, some virtual information of basket that we can describe some threefold with certain singularities and with minus 2k 0. But we don't know whether such kind of example exists. Okay, I think yeah, Miles Reed and also Gavin Brown and several people, I think they try to construct more examples by looking at the Hilbert series or something. But so far, I believe we don't have any example with minus 2k 0. Okay. So this is something very interesting, but we can not solve yet. And then for the third question, when it gives a birational map, this looks more geometry because for the theorem of Meng Chen and Rongkai Chen, they only use Riemann-Roch formula. So this looks like a purely combinatorial question actually. So you only look at when the Riemann-Roch vanish or when the Riemann-Roch has at least 2 sections or something. So this is actually their proof is purely combinatorial. But if you want to know when the minus mk gives a birational map, then this becomes a more geometry question. Okay, so then this comes to my result with Meng Chen. So we start work on this problem when I was a fresh PhD, and we can show that for if X is a canonical weak Q-Fano threefold, then the minus mk is birational for any m bigger than this 97. And if X is we assume that if X is a Q factorial terminal with pk number 1. So we met this condition many times, right? So if we assume the X has this good property, Q factorial, terminal, and pk number 1, then we can show that this 39 is enough to get this linear system to be birational. Right? So this is more. This is better. This is better than this 97. Okay, and last year we show another result. So these two results is in the paper in 2016, and in 2021 we show that if we are we're cheating a little bit. So if we are allowed to modify X by another birational model, so we can show that there exists a birational model X, which is the terminal Q-Fano 3-fold. Then if we modify X by Y, then Y we need 52 to get minus MKY to be birational. Okay. So, but this result looks not so interesting because, for example, if we consider X is a rational Fano 3-fold, then we can always take Y to be P3, right? Then we can take M to be 1. Of course, there are many non-rational X, but so that means at least this result is not so interesting for rational Fano 3-fold. Okay, so then we are always trying to improve this result. We're trying to improve this 97. Oh, so before that, let me tell you what is the conductory number. So in all known examples, we know that this example. So it already appears when we know the smallest degree, right? So this example has the smallest degree, and also it has the worst birationality. So among all examples, we know that for this example, so minus 33kx is birational, but minus 32 is not. So that means actually we might hope that this eventually we want to show that if M is bigger than 32, then minus MK is birational. Because we believe that this is the worst example to get the birationality. Okay, so in some sense, that also shows that the second result with the 39. This is not so bad, right? So this is quite close to our conjectural number, conjectural bound. But this 97 is too far from it. Okay. So then this year again with Yu Zou. So we show that we improve my result with Chen. We just show that we need 59 to get the birationality, okay, instead of this 97. Okay, so we improved from half of it, almost half of it. Okay, so of course it's also quite far from 33, but it's some improvement. Okay, and so what is the ingredient improving birationality? Okay, so birationality. So the main problem is that instead of showing birationality, we want to show when this linear system is not composed with a pencil. Okay, so here composed with a pencil means that if we look at the rational map defined by this linear system, then the image of the rational map is not a curve. So that means that the image is at least a surface or a threefold. It is not a curve. Okay. So then, so here is the result of Mengchen and myself. It shows that so if we know for some m0, oh sorry, here there's a minus sign. So if minus m0k is at least 2, and minus m1k is not a pencil, then we know that if you sum them up and take 3 times, then the 3 times m0 plus m1 is birational. Okay, so this is somehow a nice criterion for the birationality. And here we know when it is at least 2. We can take m0 to be 8 as Chen and Mengchen's result. Okay, so the only problem is we want to know when it is not a pencil, right? So if we know when m1 when minus m1k is not a pencil, then basically 3 times of it will give you a birational map. Okay, so then the problem is reduced to show that when this minus mk is not a pencil. Okay, so then let me recall what we used to detect it in old paper in Mengchen and myself's paper. So we use this theorem. So this is like a geometry inequality. Geometry inequality says that if this linear system is composed of pencil, then the H0 of minus mk is bounded from above by this linear form. The linear form is like the Rx times the volume times m plus 1. So here Rx means the Grunstein index of X. Okay, so then how to apply this theorem to tell when it is not a pencil? Then we just need to show that for m bigger enough, then the left-hand side is bigger than the right-hand side, the linear form. Then m cannot be a pencil. Okay, so then this is related to the Lima-Roche formula, right? So we can use the Lima-Roche formula to calculate the left-hand side. And of course, you know that the left-hand side is like a cubic form, right? So it's like m to the cube times the volume or something. So as long as m is big enough, then this inequality will fail. And then we know at that time we know that minus mk is not a pencil. Okay? But the problem in this theorem is that in practice, the linear form, the leading coefficient of the linear form, this r times the minus k to the cube, it could be very large. When it's large, then you need more m to break. You need a larger m to break this inequality, right? For example, when this number is 200 or something, then the number m will get very large. Then our goal is like to develop a new geometric inequality to replace this one, a better one. So we want to replace it with a better one, and this is actually okay. So your new paper, my joint work with Yu Zou. So we show that we don't need this big. We don't need r times the degree times m. And we only need 12 of it. It's okay. So we can show that if if this is a pencil, if this linear system is a pencil, then the H0 of minus mkx is bounded by 12m plus 1. And then by the Lehman-Roch, we can calculate how big m is to break this linear system. Then we can find the m1 in this theorem. Okay, so this is basically the thing we do. And yeah, here I just draw a picture to explain how we prove this theorem. I think I have 5 minutes, right? So say minus mk is a pencil. So here by pencil I mean we have a rational map from X to P1, right? So this rational map is defined by this linear system, and we can resolve it by some resolution, say W to X and to P1. And here, remember, we have another model. So this model is very useful in the proving of the upper bound of the volume. And we also apply that model here. And so we have a model from Y to S, which is also a fibration. Then you can see that this X has 2 different fibration structures. Birationally, it has 2 different fibration structures. And we can use these we can play with these 2 fibration structures to get inequalities of the linear system. So this is done by consider something like the intersection numbers and so on. Okay, so here I think the most difficult case is when S is P1 and these 2 fibrations are the same. If these 2 fibrations are the same, then we need to deal more. But if these 2 fibrations are different, then we can easily done by taking intersection numbers. Okay, so yeah, I think this is the end of my talk.